Hi. The first section examines the link between Gauss-Eureka theorem and Euler's extension of the sum of two squares theorem, showing that n is a sum of two triangular numbers if and only if 4n plus 1 is a sum of two squares. It concludes with an analog of Brahmagupta's identity for triangular numbers. The second section explores the relationship between sum of triangular numbers and sum of squares, drawing parallels to the implication of Hurwitz theorem. In 1638, Fermat claimed to have proved by infinite descent that every positive integer can be written as the sum of at most 3 triangular numbers, 4 square numbers, 5 pentagonal numbers, and more generally n polygonal numbers. In 1796, at the age of just 19, Gauss proved Fermat's claim for triangular numbers. This result became known as the Eureka theorem, as Gauss succinctly noted in his notebook. His proof uses modular arithmetic, focusing on quadratic residues and congruences. This early application of modular methods in additive number theory influenced later work on quadratic forms and partitions. Previously, in 1749, Euler proved the sum of two squares theorem, which states that any prime of a form for n plus 1 can be written as the sum of two squares. Then, in a work published in 1758, he added as a corollary: all numbers n for which a prime number is generated by the formula for n plus 1 are sum of two triangular numbers. For when 4n plus 1 is a sum of two squares, its double 8n plus 2 will be a sum of two unequal squares. Therefore, let 8n plus 2 equals the square of 2x plus 1 plus the square of 2y plus 1, so that n equals the sum of triangular numbers x and y. Thus, if n is not a sum of two triangular numbers, then the number 4n plus 1 is certainly not prime. While concise and clear, it is intriguing that Euler did not explicitly highlight the above identity, which follows easily from these simple steps. This identity was first noted by S. Realis as recently as 1885. For any parity of x and y, the expression x plus y plus 1 and x minus y will always have opposite parity. One will be odd, the other even, thus matching the odd parity of 4 times the sum of triangular numbers x and y plus 1. Notably, these expressions also emerge naturally while deriving an alternative formula for Pythagorean triples in our previous presentation: Pythagorean triples, triples, consecutive sums, and pyramids. Notice that in this formula for Pythagorean triples, the factors x plus y plus 1 and x minus y appear in the third square, while in the second square, 2x plus 1 times 2y plus 1 equals the difference of squares x plus y plus 1 and x minus y. This allows the formula to be naturally rewritten in a familiar form. Next, we'll revisit Euler's corollary through the lens of the above identity, this time examining both prime and composite integers. Our focus is on two key questions. Does this identity account for all integers expressible as a sum of two squares? And can an integer n be written as a sum of two triangular numbers if 4n plus 1 cannot be written as a sum of two squares? We first recall the previously established identity. Given n equals the sum of triangular numbers x and y, we expand and regroup the terms. Then add and subtract 2 times x times y to complete the squares, recovering the previously presented identity. For any combination of odd and even values of x and y, the expressions x plus y plus 1 and x minus y will always have opposite parity, one being odd and the other even. Thus, this identity accounts for all integers that can be written as a sum of two squares. To clarify this, we can reformulate the identity by introducing new variables. Let a equals x plus y plus 1 and b equals x minus y. This gives us the relations a plus b equals 2x plus 1 and a minus b equals 2y plus 1. Solving for x and y, we obtain x equals half the value of a plus b minus 1 and y equals half the value of a minus b minus 1. Substituting this into our original identity yields this expression, where the sum of the squares of a and b equals 1 plus 4 times the sum of the triangular numbers a plus b minus 1 over 2 and a minus b minus 1 over 2, where a is bigger than b. Here, a and b must have opposite parity for a squared plus b squared to be odd, aligning with integers of the form 4n plus 1. Assuming a is odd and b even, we write a equals to c plus 1 and b equals to d. Then a plus b minus 1 over 2 equals c plus d, and a minus b minus 1 over 2 equals c minus d. Since a is bigger than b, it follows that c minus d is a positive integer, ensuring both expressions remain integers. The same reasoning applies if a is even and b is odd. Thus, this reformulated identity accounts for all integers that can be written as a sum of two squares, expressing n as a sum of two triangular numbers with integer variables. Last, can an integer n be written as a sum of two triangular numbers if 4n plus 1 cannot be written as a sum of two squares? An integer of this form can be decomposed in its prime factors, where p sub I are primes of the form for k plus 1 and q sub j are primes of the form for k plus 3. That is, while an integer 4n plus 1 may also have prime factors q sub j, as long as they have even exponents, then said integer can be expressed as a sum of two squares. However, if 4n plus 1 has a prime factor q sub j with odd exponent, it will be congruent to 3 modulo 4. Thus, 4n plus 1, to remain of the same form, it must include another prime factor with the same properties so that the product is congruent to 1 modulo 4. Factoring out all prime factors p sub I, we obtain an integer of the form 4n plus 1 with only factors for k plus 3. Grouping these factors in pairs, each product results in an integer of the form 4n sub q plus 1. Now, if n sub q could be written as a sum of two triangular numbers, then 4n sub q plus 1 would have to be expressible as a sum of two squares. However, Euler's two-squares theorem states that only primes of the form 4k plus 1 and prime factors of the form 4k plus 3 with even exponents can be expressed that way. Since this contradicts our assumption, we conclude that an integer n can be written as a sum of two triangular numbers if and only if 4n plus 1 can be expressed as a sum of two squares. To end this section, we verify that the product of two integers of the form 4 times the sum of two triangular numbers plus 1 results in another integer of the same form. Just as the product of two sum of squares yields a sum of two squares in two distinct ways, the same holds for the product of two integers of the form involving triangular numbers. To demonstrate this, we recall the identity established earlier. The Brahmagupta's identity shows that the product of two sums of two squares remains as sum of two squares in two distinct ways, yielding pairs u sub 1, v sub 1, and u sub 2, v sub 2. From these, we compute u sub 1 plus v sub 1 minus 1 over 2, and u sub 1 minus v sub 1 minus 2 over 2, and the same for u sub 2, v sub 2. We can present this more clearly, but first recall that the triangular number minus w equals the triangular number w minus 1. This ensures that a triangular number minus w is always a positive integer, or 0, for any positive integer w. When expressing the product in both possible forms, we notice that in the second case, q sub 2 might take a negative value. However, this poses no issue, as it corresponds to a valid positive integer under the given identity. These are possible ways to express p sub I and q sub I involving the terms of the squares, revealing elegant symmetries. Finally, let's look at an example, 721,421, the product of 953 and 757, where both are prime factors of the form 4n plus 1. First, we determine the representations as sum of two squares, using the infinite descent method presented in previous videos, and then use those values to compute their corresponding triangular numbers. For 953, the triangular numbers pair is 20 and 7, and for 757 it is 17 and 8. Second, to find the triangular numbers for 721,421, we can follow two different approaches. The first applies Brahmagupta's identity, yielding two sum of squares pairs, 845 and 86, and 611 and 590. From these, we compute the triangular number pairs, 465 and 379, and 610. The second approach directly applies the expressions presented earlier using the triangular number pairs 20 and 7 and 17 and 8 from the prime factors. This method leads to the same triangular numbers, but works strictly within the triangular number framework, avoiding the intermediate steps of dealing with squares. In conclusion, as a corollary of his sum of two squares theorem, Euler noted that any number n for which 4n plus 1 is a prime number can be expressed as a sum of two triangular numbers. While his argument is clear and direct, it is surprising that Euler did not explicitly highlight this identity. Interestingly, the expressions x plus y plus 1 and x minus y have also emerged naturally while deriving an alternative formula for Pythagorean triples. We revisited Euler's corollary through the lens of this identity, extending the analysis to both prime and composite integers. First, we verified that the identity accounts for all integers expressible as a sum of two squares through this other identity. We then disproved the possibility of writing n as a sum of two triangular numbers when 4n plus 1 cannot be written as a sum of two squares. Additionally, we derive an unexpected analog of Brahmagupta's identity for triangular numbers, offering three distinct ways to express p sub I and q sub I by combining the expressions for the square terms of the factors. Finally, we illustrated it with a detailed example. Hurwitz' theorem states that if a quadratic form preserves multiplication when mapping numbers to positive real values, then the only possible number systems that allow this are the real numbers, complex numbers, quaternions, and octonions. No other number system possesses this property. A significant consequence of this theorem is that multiplication formulas for sum of squares can only exist in dimensions 1, 2, 4, and 8, as this corresponds to the only number systems, known as division algebras, that permit such multiplication rules. In this section, we introduce an unexpected connection between the sum of triangular numbers and the sum of squares, one that rhymes with the consequences of Hurwitz' theorem. Extending the identity derived in the previous sections to sum of 2 raised to n squares reveals a gradual decline in coverage and an increase in constraints when expressing triangular numbers in terms of squares. While the pattern holds for sums of 1, 2, 4, and 8 squares, it ultimately breaks down at 16 squares. There are 4 identities involving sum of triangular numbers. The first connects the sum of consecutive integers to a perfect square. The second corresponds to Euler's sum of two squares theorem, dealing with prime factors of the form 4n plus 1, as discussed in the previous section. The third links Gauss-Eureka theorem and Lagrange's 4-square theorem. The fourth is tied to Degen's 8-square identity. Extending the identity beyond n bigger than 3 introduces fractions in sums of triangular numbers, as seen in the n equal 4 case below, which connects to Sedenions. However, the real trouble arises when reformulating these identities by introducing new variables for the square term expressions, as we did earlier for the sum of two squares. We can also reformulate these identities by introducing new variables for the expressions in the square terms, just as we did in the previous section for the sum of two squares. For n equals 0, we got this identity. We can reformulate it in terms of x, requiring two expressions, one for odd x and other for even x. For n equal 1, we obtain the identity revealed in the previous section. For n equal 2, we take the squares 2, 3, and 4 as variables x, y, and z, leading to the neat relation x plus y plus z plus 1 equals a plus b plus c plus 1, that is, the first square. Additionally, we have 2a equals y plus z, 2b equals x plus c, and 2c equals x plus y. This results in an elegant identity that extends to a broader range of integers compared to the identity using variables a, b, and c. Note also that the sum of these three triangular numbers is equivalent to the sum of the triangular numbers x, y, and z, and x plus y plus z. Substituting this into the previous equation yields a highly symmetrical and elegant identity. Furthermore, we can derive two additional identities yielding similar results. The first involving the odd squares 2, 3, and 4, and the second involving the even squares 2, 3, and 4. For n equals 3, we choose the squares 1, 6, 7, and 8 as variables x, y, w, and z. Linear combinations of these result in 4a, 4b, 4c, and 4d on one side, and the remaining squares 2, 3, 4, and 5 on the other. This leads to a neat identity involving variables x, y, w, and z. Note that for the last four squares, the sum or difference of x, y, w, and z must be an odd integer. Additionally, three of these squares involve two terms with negative signs, while the remaining square has no negative terms. All of them include -1. Also, for n equals 3, we can deduce a related identity. In this case, 4 of the squares are half values, as seen in the reformulated identity previously discussed. However, this time, there is only one negative sign in each square, with all of them including +1 instead of -1. Here, we assume that a plus minus b plus minus c plus minus d must be odd to ensure integer values. This requires three of the terms to share one parity, while the fourth being of the opposite parity. When choosing the last four squares as x, y, w, and z, and proceeding with the substitution, we arrive at a new identity that mirrors the previous one, but with -1 instead of +1. Note that in this case we are dealing with sum of triangular numbers that only needs to be divisible by 2 instead of 4 as in the earlier case. The last case is n equals 4, involving 16 squares. In this case, we choose the squares 7 to 16 as variables. There are 10 variables: u, v, w, x, y, f, g, h, j, and k. Linear combination of these allow us to substitute 8a, 8b, 8c, 8d, and 8e, along with the remaining squares 1 to 6. This results in a highly elegant identity with 10 variables, where the triangular numbers need to be divided by 4 instead of 8. What are the consequences of reformulating the identities with new square term variables? Hurwitz' theorem limits the existence of norm division algebras to dimensions 1, 2, 4, and 8. As n increases in sum of 2 raised to n squares, key algebraic properties are progressively lost. For n equals 0, that is, reals with one dimension, all fundamental properties hold: ordering, commutativity, associativity, and distributivity. For n equals 1, that is, complexes, 2 dimensions, order is lost, but commutativity, associativity, and distributivity remain. For n equals 2, that is, quaternions, 4 dimensions, commutativity is lost, though associativity and distributivity are preserved. For n equals 3, that is, octonions, 8 dimensions, associativity is lost, but a weaker form, alternative associativity, remains, along with distributivity. For n equal or bigger than 4, that is, sedenions and beyond, 16 dimensions or more, alternativity is lost. Just power associativity holds. Plus, 0 divisors appear, so no norm division algebra exists. When mapping squares back to triangular numbers, we'll show that as n increases, the coverage of integers shrinks, while parity and sign constraints tighten, a progression that rhymes with Hurwitz' theorem. For n equals 4, equality breaks down when variables are freely redefined. For n equals 0, one square term, we can map all positive integers square values with one formula for odd numbers, another for even ones. Numbers of the form a times the triangular number plus 1 are multiplicatively closed. the product of any two such numbers remains in the same form. This holds for all cases, both odd, both even, and one odd with the other even. When mapping one square back to triangular numbers, n+1 variables are required, allowing a full mapping of integers. As we showed, the form 8 times a triangular number plus 1 is multiplicatively closed. Also, the left-hand side equals the right-hand side. For n equal 1, that is, two square terms, we can map any sum of two positive squares that yields an odd integer, but order matters. While x squared plus y squared is equal to y squared plus x squared, ensuring non-negative triangular numbers variables requires enforcing that x is equal or bigger than y plus 1. Since an odd integer of the form for n+1 requires x and y to have opposite parity, then the condition x plus minus y minus 1 all over 2 is automatically satisfied. Numbers of the form 4 times the sum of two triangular numbers plus 1 are multiplicatively closed. The product of any two such numbers remains in the same form, as we demonstrated in the previous section. Here we have two possible ways to write this product in this form. So for n equal 1, the only difference is that ordering is required to avoid negative values. All other properties remains unchanged. For n equal 2, that is 4 square terms, we can map any sum of three triangular numbers to a sum of 4 squares, that is, an odd integer 2k plus 1. Since this accounts for all combinations of odd and even triangular numbers, Gauss-Eureka theorem ensures we cover all integers. Consequently, the 8 possible cases, listed below, correspond to combinations of 4 squares that represent all odd integers 2k plus 1 following Lagrange's 4-square theorem. When allowing negative values for x, y, and z, we ensure full coverage of all integers in a single identity. By examining the behavior of positive and negative signs across all 8 cases, we see that permitting negative values for x, y, and z guarantees complete coverage of all integers within a single identity. Unlike Brahmagupta's identity, a full analog of a 4 squares identity does not extend to triangular numbers under the same algebraic structure that worked for n equals 0 and 1, as numbers of the form 2 times the sum of three triangular numbers plus 1 exhibit only restricted multiplicative closure. Under this condition, we can establish specific cases where the analog remains valid. Just as we used Brahmagupta's identity for n equal 1, we now apply Euler's 4 squares identity for n equal 2, adopting the sign convention that became standard after the discovery of quaternions. Our goal now is to find expressions for alpha, beta, and gamma in terms of linear combinations of u, v, w, r, s, and t. Since the product of two such numbers of the form involving sum of three triangular numbers must result in a sum of 4 squares, f, g, h, and j, the natural move is to analyze the difference. This pays off, yielding the difference of squares f plus g plus h plus 1 and j. Simplifying, that leads that the product of two numbers of this form must equal f squared plus g squared plus h squared plus the square of f plus g plus h plus 1, which in turn equals 1 plus twice the sum of triangular numbers f plus g, f plus h, and g plus h. This observation allows us to naturally extend the result to three other triplets of the triangular numbers. Under these conditions, we obtain constraints involving the original variables u, v, w, r, s, and t. In this other slide, we can see some examples of these conditions. This becomes clearer with an example. We will use the same integer used in the previous section, 721,421, the product of 953 and 757. Note that 953 has 120 solutions as a sum of 4 squares in the form of u, v, w, and u plus v plus w plus 1, which are not easy to find, by the way. Similarly, 757 has 144 such solutions. So we need to select one solution out of over 17,000 possible combinations. In fact, there are 6 valid combinations for the product, which involve the same magnitudes but 2 signs variations for R, S, T, R plus S plus T plus 1, and U, V, W, U plus V plus W plus 1. We'll examine 2 of those solutions, the ones that yield different magnitudes for alpha, beta, and gamma. In solution 1, we express both 953 and 757 as 2 times the sum of 3 triangular numbers plus 1. Then, we apply the 4 squares identity using the given values and verify that f plus g plus h plus 1 equals j. We also confirm that the identity involving u, v, w, r, s, and t holds. This let us express 953 times 757 as 2 times the sum of 3 triangular numbers plus 1, illustrating how the product of 2 integers in this form yields another integer of the same form, provided the necessary conditions are met. We also look at solution 2, which gives different values for the resulting triangular numbers. To summarize, for n equal 2, ordering is necessary. Allowing negative values ensures a complete mapping of integers through a single identity, but there is limited multiplicative closure for the form 2 times the sum of 3 triangular numbers plus 1. For n equal 3, 8 square terms, we can map a subset of sum of triangular numbers, specifically those of triangular form for m or for m minus 1, into a sum of 8 squares. When mapping squares back to triangular numbers, the condition plus minus x plus minus y plus minus w plus minus z must be odd to ensure integer values, restricting the mapping to even triangular numbers. Furthermore, to prevent negative triangular numbers, the constraint z equal or bigger than x plus y plus w plus 1 must hold. Nevertheless, for n equals 3, we can relax the restriction. Instead of mapping sums of triangular numbers of the form for m or for m minus 1, we can extend it to those of the triangular form 2m or 2m minus 1, provided that 3 of the variables m sub I share one parity while the fourth has the opposite parity. That is, a plus minus b plus minus c plus minus d must be odd to ensure integer values. Consequently, rather than working with for a, for b, for c, for d, we now consider expressions like for a prime, for b prime, for c prime, and 2d prime, or 2a prime, 2b prime, 2c prime, and 4d prime. When mapping back squares to triangular numbers, the condition that plus minus x plus minus y plus minus w plus minus z be odd is equivalent to the previous constraint. Even though a sum of 8 squares can be mapped back to a sum of 4 triangular numbers plus 1, either in the form for m minus 1 or 2m minus 1, and despite Deegan's 8 square identity holding, multiplicative closure fails in all cases for any combination of I, j, k, l from 1 to 8. To recap, for n equals 3, the mapping of integers becomes restricted, parity constraints arise, and the form is no longer multiplicatively closed. For n equals 4, 16 square terms, only a subset of sum of triangular numbers, specifically those of the form 8m or 8m minus 1, can be mapped into a sum of 16 squares. Unlike previous cases, where n plus 1 variables suffice to map back the squares to triangular numbers, this case requires 2 times n plus 1 variables. In addition, this expression involving the 10 variables must be even, which holds if all variables share the same parity, if 8 have one parity and 2 the opposite, or if 6 have one parity and 4 the opposite. Note that there are 6 possible combinations of 5 pairs that satisfy the identity. Moreover, when replacing the 10 variables with a lowercase counterpart which no longer represent linear combinations of A, B, C, D, and E, the left-hand side no longer equals the right-hand side, unlike in previous cases. Below, we display the 10 required terms instead of u, v, w, x, y, f, g, h, j, k to ensure the left-hand side equaling the right-hand side. To summarize, for n equals 4, twice the number of variables are required, that is 2 times n plus 1. And a fundamental condition that the left-hand side equals the right-hand side is not even satisfied. In conclusion, this identity exhibits a progressive decline in coverage and an increasingly restrictive conditions as triangular numbers are expressed in terms of squares. While the pattern holds for some of 1, 2, 4, and 8 squares, it ultimately fails at 16 squares. As n grows, reformulating the identities using new square terms variables reduces coverage and tightens parity and sign constraints. Unlike earlier cases where n plus 1 variables suffice to map back the squares to triangular numbers, the case n equals 4 requires 2 times n plus 1 variables. Moreover, when replacing the uppercase variables with the lowercase counterparts, which no longer represent linear combinations of the triangular number variables, the left-hand side no longer equals the right-hand side. A full analog of Brahmagupta's identity for triangular numbers is achieved at n equal 1. A limited form of multiplicative closure is observed for n equal 2. The property does not appear to hold at n equal 3, and it certainly fails for n equal 4, given the left-hand side, right-hand side mismatch described above. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.